everyone. Welcome to the lecture on linear regression. So in this video, we're going to talk about how to use linear regression and what is the model construct and how the model is developed. All right, so simple linear regression is the simplest form, right? So we just talk about the linear part. Linear means that it is a straight line, right? It's a straight line. So as we recall from high school knowledge, the way we represent a linear line is by two coefficients, right? So we have the intercept, which we denote as beta 0, and then plus slope beta 1 times the variable, the independent variable x, and then we denote it as y. So y is it's a line, right? It's a straight line, and then we can denote it as this form. So this is called the point slope form, right? So we have a point and we have a slope. So example, if I want to express maybe this line, right? So this passes across to what is the form of for this line? I can express y equals to I know that it passes this point of 2, so beta 0 is 2, right? And then plus maybe it's just x, so beta y is 1. All right, so this is the form of this linear line. All right. The question is, in the linear regression world, these beta 0 and beta 1 are not known, right? They are something we need to estimate based on data. So the setting is that now our data is looks like this. So for example, we have x and we have y, and maybe when x to 1, y equals to 2, x equals to 2, or y equals to 2.5, etc. Right? So these are the so-called training data. Of course, in this case, we only have one x, we only have one so-called independent variable, which makes it easy for us to plot it on the graph. Right? So plus x, y here. So I have multiple points, which may look like this, right? So we have a bunch of points, and each point will have the coordinate. So this coordinate may be 1, 2, maybe this is 1.1, 2.5, right? Each point has a coordinate. It's corresponding to the value of x and y. Now, the purpose of linear regression is really to fit a line. So this kind of line could be like this. Just drawing an arbitrary line. We can only draw a line because it's a linear model, right? There's nothing we can do. It cannot be a curve. So this is line. But in the linear regression, it is a model, right? So talk about a model, and a model needs to go through some sort of optimization process, right? So it needs to be optimized so that we have a so-called optimal model. So now the question boils down to what is the value of beta 0 and beta 1 such that the model is optimal, right? So optimal model, which further corresponds to the cost is minimal, right? So I want to have a model such as the cost is minimal, because we need to have some notion of what is optimality. Now we see that the model that has the lowest cost is the optimal model, right? So now what is cost? So cost is defined as, in this case, it's the distance between the prediction and the true target, right? So what does that mean? This is my true target. This is my real value I want to predict, right? So if I can make this line a curve, right? If I can draw a curve that passes through every point, right? This would be a perfect model because it can give me 0 error, because this model passes through all the points in the data. But this may not necessarily be something I want, because this is a clear sign of overfitting, which we'll be talking about in the future videos. All right, so in this case, I can only draw a line, and this is my y here. This is my true value, right? This is my y, and my corresponding prediction which I denote as y hat. Y hat is here. So all the predictions can only live on the line, right? Because the line itself is a prediction. So every any point in the on the line is a prediction corresponding to the point x, right? So give x, then can find the corresponding y hat, and then if that's a true value, then this distance is there is the error, right? Which we denote as epsilon. So this is the error. In other words, when I want to express the so this is actually my y hat, right? My y hat. So for the true y, which is the value I'm trying to predict, it is actually consists of the y hat, right? Plus the error term epsilon, right? Or we can just plug in beta 0 plus beta 1 x plus epsilon, right? So this is the prediction. This is the true form. This is the form of the model we are using, right? We are trying to use a linear regression model, and we know that's not all, so all the models are wrong. They are wrong because there's this extra error term here. So we have the error term, we have the prediction, then jointly they give the real value y, right? So that's something we're doing here. So let's come back to the cost. So this is just one point, right? So one point. Of course, we have multiple errors, and we need a way to aggregate all these individual errors, right? So so this is, for example, this is let me just use the index, right? This is error 1, right? Error 2, error 3, right? So this index denotes the number of the sequence of the points we have in the training set, right? So now we can say that, oh, I can sum up, so I'm sum up some at epsilon 2, etc., all the way to epsilon n, right? Assume I have total n points. But the question is, the problem is error 1 and error 2 may cancel each other, right? So if they have opposite sign, then they would cancel each other. And this is something we do not want to have, because if they cancel each other, we have no idea what is the true error, right? So that's one way, which is to take the absolute value, which is not so common. So the more common is to say, I can take the square of all the errors, so that's now at least they have the same sign, which are all positive, right? And then I sum them up. So then I define my total cost, which is L, right? L usually stands for loss, right? So I just use the term, the notation L. For total error, total loss is the sum of all the individual points squared, right? In other words, I can also say express this in more succinct form. So I from 1 to n, right? This is just summation notation. So I'm summing from n to n. Summing which one? Summing the epsilon, right? So the error terms. This each error term I square it, and then I sum it up. Right? So this is my loss. All right, and now I just want to minimize it, because I want to have the model which is minimized. So this is minimize this error, and my error and my loss is actually a function of beta 0 and beta 1 now. Right, so we talk about, we can view everything as a function. In this case, my input is a specific value of beta 0 and beta 1, right? My output is just one error. So the question is, how can I find the value of beta 0 and beta 1 such that the error is minimized? Right? So this is the objective of linear regression, right? Okay, so now let's look at how this could be done in the linear regression class, right? So just a simple illustration, we can use the linear regression package from the sklearn, right? Typically, what we do is just to instantiate the class into an object, right? So this is class, and we have object here, which is called LM, and we can call the fit method based on the training data we have. With the training data, we need to pass in the X and Y. Fit means that now we're training the model. So now the beta 0 and beta 1 are optimized, right? So we can extract the beta 0 and beta 1 here, right? So these are beta 0 and beta 1, and then we can use that to make predictions for the new input X. So we have a new input X, just passing, then use the predict method. Again, note that this is a class, right? So talk about class. A class has two things, right? So it has functions, also called method, right? So in terms of the things it can do, and so we also have the attributes. So these are the components, right? So those attributes are things like intercepts, call if, right? So these are attributes. Functions or methods looks like fits and predicts, right? So they are specific procedures that the object can perform. Again, the class it's just abstract, that it will go into an object, which makes it concrete, right? So with concrete things, now we can call the functions, the methods, and the attributes, right? So understanding the results. Now, the result itself is actually, so let's talk about, in the previous case, we have some dots here, right? And we are going to fit a line. So this line, when we look at this one, so this is the actual target y, right? Maybe this for the ith point, so yi, and this is my y hat for the ith point. And if I just draw one more line, which is called y bar. Y bar represents the average value of the data we have. So it's just defined as all the points summed together, right? So I take all the points of y and then sum together, and then take the average, right? So this is just the average y value in my data, right? So so how do we measure? So it's different problem. They have different x and y's, but we need a sort of uniform metric to measure how good the model is, right? So that's one metric called R square, right? R square means the proportion of the variance that is explained by the model, right? The proportion of the variance observed in the data that is explained by the model. So that's very abstract. So let's just dissect the definition, right? So I need to get the variance of the data, right? This is the total variance I want to explain, because if I know how to explain the variance, right? If I know how the data varies from one to another, then I can predict it perfectly, right? So this is the variance of data, and we learned from basic statistics how to calculate the variance, right? So you can say for each point, take the distance between the points and the average value, right? So and then I just take a square and sum it up so that I have all the squared distances, and then take the average, right? So this is my variance, which I can denote as sigma square. Right, so this is the definition of the variance, and then this just measures the squared distance on average, right? So this is the variance of the data. How about the variance, the var of the noise, the epsilons, right? So the errors. So why do we need to have the average, the variance of the errors? So the error is here, right? We talk about error, which is here. Now this is error that represents the sort of the space that we yet to explain, right? We yet to improve the model. They want to say if the error is very small, then that means the model is very good, right? So we want to also measure in terms of how good the model is using the metric of the error, right? And then again, we are living the space of the variance. So we need to reduce the variance, and then we want to look at the variance of the error term. The error term is yi minus y hat I, right? So this for 1 point. Again, we take the square, right? So square roots, square roots, and then add them up. Then take the average, right? So this is the variance of the error. Now, coming back to the definition of the R square. So this is defined as 1 minus the proportion, right? So we talk about the proportion. This is the proportion where we in the numerator have the variance of the error terms, like y minus y hat. So this is the error terms. Okay, and then have again, this is the variance of the data itself, right? So I have the 1 over n here, which can cancel out, which is fine, right? So which means now this is the variance that I yet to explain, right? So this represents a proportion of the variance in the data that I yet to explain. I take the 1 minus, which means this represents the explained variance, right? Variance, explained var. Okay, in terms of proportion. So proportion, we need to have the proportion because now it can give us a sort of a measure that we can compare across different results, across different models. So the result, so the value of R square will be a value between 0 and 1, right? So it's a value between 0 and 1. So if the value is big, like for example 0.9, we see that we can explain using the linear model 90% of the variance of the data. Right? So that's what it's about. All right. So we can also look at multiple linear regression. Multiple linear regression is just taking more predictors. So in this case, we have y here. We'll have maybe just use y hats. These are prediction. Beta 0, beta 1 x1 plus beta 2 x2, right, b beta k xk. Right. So we have this many beta here, which means we have more than one independent variables. When that's the case, we call it the multiple linear regression, right? So the only thing to take note here is that multiple linear regression, we need to pay attention to the way we interpret the results, right? So when we see that because we have so many moving parts, so x can move x1, x2, this represents the features of the data, right? We need to see that when we are moving certain feature, for example, x2, we give it a small increment, like from delta x, right? So x2 becomes x2 plus delta x. Now we need to see that when that's the case, when x2 increases by a small amount, and we control for other features, so all the other features, they stay fixed, right? They stay fixed. Now we can say what is the impact on the resulting y here. So there'll be a small increment for y, and then this increment is purely due to the increment in x, and provided that we control all other variables unchanged. Right? So this is also called the ceteris paribus analysis, which means that all others being equal, right? So all the rest of the factors being equal, now we're only going to change x2, right? So that's the point we need to pay attention here. Okay, so again, let's look at implementation. It's very straightforward. So we just use the log to extract a series of columns. So in this case, we are going to extract columns between TV and newspaper. So there will be multiple columns here. And then we're going to take ceos as our y. Right? So these are x, these are y. We pass to the linear regression class, which got this name, and then we use the fit method to train the model. So later we're going to talk about what happens when we call the fits, right? And then we can extract the intercept coefficients, which will be more than 1, and then we can use a score method to say what is R square, right? For the data we have. That is just to calculate the R square using the score function. Right. So alternatively, we can use we can use another method which is from the stat model package, right? So which is more versatile. So say in this case, we're going to prepare some data sets. This is just some filtering, and then we can use this syntax, which is very similar to the syntax of R, right? R when you do a linear programming, linear modeling, right? So we're going to treat price as our y variable and area plus type as our input variable. And again, we can fit and then look at the summary of the model. So in terms of results, so you get this table, and the most important thing to take note here is that first R square, right? It is so this means that it explained 82% of the data, of the variance of the data, right? And then here we have beta 0, beta 1, and beta 2, which represents the coefficients for area, for type, for the intercept, right? And then this is our coefficient values. So this standard error, which is to say that we have the estimate, which is coefficient, but also the error, right? There's an error for estimation. And this is the range of the values that the estimate can vary, right? Based on certain confidence level. So what I mean is that, for example, for this one, it is so this is a value, and confidence interval just make it as a range, right? This is a range, and this is y. This is at 2.5% and 7.5%. So which means that's I'm 95% sure that the value of area, the coefficients will live inside this range, right? And then another thing is the p-value. So if it is small, then it means that the value we're seeing, it is significant, right? So otherwise, if it's too big, then it means it fails a statistical test, and then we cannot really use the results we are seeing here. One more thing is the interaction term, which represents the possible impacts from different sort of crossover effect, right? So next is y could be again I just express y hat, right? So beta 0 plus beta 1 x1 plus beta 2 x2. So the interaction term says that maybe x1 x2 there's a crossover effect. The y will be somehow different depending on the specific combinations of x1, x2. Right? Next is if we want to model this, then we can add a new term, which is x1 times x2, right? So this represents the interaction effect between the two values. Another aspect is the so-called nonlinear term. Right? So nonlinear term means that the terms in x is not linear. So y could be represented as beta 0 plus beta 1, x1, then plus beta 2 x1 squared, right? So this term, this x1 squared is totally derived based on the x1, right? So we only need to know x1 to derive x2, x1 squared. So this is additional feature derived, or you can call it feature engineering, right? So, but now this is a term that is nonlinear because this is squaring effect. If we square it, then it becomes nonlinear, right? Because it's a curve now. So it is nonlinear, but we see that it is still a linear model because the coefficients are still linear, right? So it's still a linear model. It is only we are catering for the nonlinear terms in x. Okay. So all right, so that's it for this video, and in the next video we're going to derive look into the process of obtaining the coefficients for the linear regression model, which we also call the closed form solution, right? Right, so that's it for this video, and thanks for watching.